Please subscribe to support the channel. The universe is full of strange wonders. Spiral galaxies that swirl like cosmic hurricanes, elliptical galaxies that resemble hazy celestial clouds, and irregular galaxies that look more like scattered debris than structured systems. But every so often, astronomers stumble upon something that doesn't just look unusual. It challenges our very understanding of how galaxies can exist. One of the most extraordinary examples of this is a cosmic enigma known as Hoag's object, a galaxy so unusual, so eerily symmetrical, and so perplexing that many astronomers describe it as one of the greatest mysteries in the visible universe. This galaxy doesn't just catch the eye, it unsettles the mind. When scientists first laid eyes on it, the reaction wasn't simply wonder, it was disbelief. Galaxies are supposed to follow certain rules. Spirals form from density waves and rotating disks of stars. Ellipticals take shape from ancient collisions that smear stellar matter into smooth ovals. Irregular galaxies are messy products of disruption and gravitational chaos. But Hoag's object? It refuses to play by these rules. Instead, it presents a cosmic puzzle, a glowing, perfectly rounded yellow core, suspended like a pearl inside a flawless, luminous blue ring. Between them, a mysterious gap of empty space, as if the universe itself had carved out a moat. Why is this so shocking? Because symmetry on such a scale is nearly impossible in nature. Galaxies are turbulent. They twist, bend, and distort over billions of years under the influence of gravity, dark matter, and cosmic collisions. Yet here lies Hoag's object, calm, balanced, and geometrically pristine, as though painted by a celestial artist's brush. The sight of it challenges our intuition, whispering that maybe our rules about galactic formation are incomplete, or worse, that we don't truly understand the dynamics of cosmic evolution at all. It is not merely the beauty of Hoag's object that makes it famous, it's the defiance it represents. This galaxy doesn't just look different, it forces astronomers to confront uncomfortable questions. Could there be processes at work in the universe we haven't yet discovered? Are our models of gravitational resonance, galactic collisions, and star formation missing crucial details? Or is Hoag's object simply an extraordinarily rare accident of cosmic chance, a one-in-a-billion masterpiece carved from the raw material of stars and dust? When Arthur Hoag first spotted it in 1950, he himself could hardly believe what he was looking at. To him, it looked like an oddball that didn't fit into any galactic category known at the time. And decades later, even with the most advanced telescopes humanity has ever built, the mystery remains unsolved. Astronomers can propose theories, but none can explain it fully. The galaxy mocks our efforts, remaining elegant, silent, and inexplicable across the vast gulf of 600 million light-years of space. This is why Hoag's object is more than just another item in a star catalogue. It's a cosmic riddle that reminds us of a humbling truth: the universe still holds secrets we can barely begin to grasp. Each time we look at it, we're forced to admit that our knowledge is still in its infancy. It's a glowing signpost pointing toward the unknown, challenging us to keep asking questions and to keep reaching for answers. When you first hear that Hoag's object is unlike any galaxy we've ever seen, it's easy to imagine it as just another oddly shaped smudge of light, the kind that fills astronomy textbooks with faint pictures and scientific jargon. But the reality is far more breathtaking. Once you lay your eyes on an image of this galaxy, everything clicks. You immediately understand why it has fascinated astronomers for decades. Hoag's object doesn't look like a mess of stars pulled into strange spirals, nor does it resemble the featureless blur of an elliptical galaxy. Instead, what you see is something so clean, so geometrically precise, that you almost forget you're looking at a natural object shaped by random forces. At the very heart of Hoag's object sits a compact, golden yellow sphere of older stars. This bright core glows like a miniature sun, but on a galactic scale. It isn't stretched or twisted. It isn't smeared by gravitational tug-of-war with nearby galaxies. It's simply round, like a perfect bead of light. Surrounding it is not the dense spiral arms we expect, nor the faint halo of dust we often see in ellipticals. No, the central core sits almost in isolation, suspended within a nearly perfect void, a wide band of nothingness that separates it from the galaxy's most striking feature, its flawless outer ring. That ring is what makes Hoag's object iconic. Stretching around the golden core is a luminous circle of blue stars, so vibrant and uniform that it looks painted. These stars are young, massive, and extremely hot. Astronomers know this because their blue glow is a hallmark of youth. Unlike the old stars in the core, which have long burned through their brightest fuel, the stars in the ring are newly ignited beacons of cosmic energy. They're scattered evenly along the circumference of the ring, almost as if some invisible hand placed them in their positions to create this symmetrical outline. The contrast is what makes Hoag's object both scientifically intriguing and aesthetically captivating. The golden yellow of the central sphere suggests age, maturity, and stability. The radiant blue ring represents vitality, birth, and new beginnings. And between them lies a dark, empty gap, an interstellar moat that deepens the mystery. Why is there such a separation between the old and the new? What prevented the stars from filling the void between the core and the ring? These questions have stumped astronomers since the object was first identified, and they continue to fuel research today. To put the appearance into perspective, imagine the difference between looking at a typical spiral galaxy, with its winding arms filled with stars and dust, versus seeing Hoag's object. In spirals, there is always a sense of motion, arms stretching outward like whirlpools frozen in time. But Hoag's object looks almost static, almost mathematical in its perfection. The blue ring is smooth, uniform, and circular in a way that seems more like an artist's design than a chaotic product of nature. The first time the Hubble Space Telescope captured high-resolution images of Hoag's object, astronomers and the general public alike were stunned. The photos looked less like astronomical data and more like a work of surrealist art. Some described it as a cosmic target in space, a bullseye painted across the canvas of the cosmos. Others compared it to a celestial donut, though one far more pristine than any pastry could ever hope to be. And while these playful nicknames help capture its strange beauty, they don't fully convey just how profoundly unusual this galaxy is compared to what we expect from galactic structures. Another feature that makes the appearance so remarkable is just how isolated it seems. Hoag's object is not surrounded by close galactic neighbors that could easily explain its shape through interaction. Many galaxies with rings or odd structures are the product of violent collisions or nearby gravitational influences. But Hoag's object floats alone, at least in the local cosmic neighborhood we can see. Its near-perfect symmetry seems even more uncanny given this solitude. There's no obvious culprit, no nearby companion galaxy tearing at its edges to produce the ring. It sits there, self-contained, a riddle wrapped in cosmic beauty. And the perfection doesn't end with its basic outline. The width of the ring, the separation of the gap, and the scale of the golden core all fit together with such harmony that it almost looks intentional. Of course, scientists don't invoke intention, they look for physical explanations. But the sheer symmetry challenges those explanations. Galaxies are supposed to be messy. They are supposed to evolve chaotically over billions of years. They are supposed to bear the scars of collisions, gravitational distortions, and the pull of dark matter. Yet Hoag's object seems to have defied that chaotic destiny, preserving a structure that looks more like geometry than astrophysics. This striking appearance is also what first drew Arthur Hoag's attention back in 1950, when he peered through his telescope and noticed something odd, a glowing core with what appeared to be a faint, detached ring around it. At the time, photographic technology wasn't advanced enough to capture its true detail, but even then, its odd form stood out. Decades later, as imaging improved, the full majesty of Hoag's object was revealed, cementing its status as one of the most remarkable sights in the cosmos. But what makes this description more than just poetic observation is the fact that the physical appearance of Hoag's object hints at deep, unanswered questions. The golden sphere at its center tells us about ancient stellar populations. The blue ring screams of recent star formation. The gap in between is a silent void begging for an explanation. Why didn't gas and dust fill that space? What physical process could have stripped it clean? If a collision caused the ring, why do we not see the messy aftermath that such interactions usually leave behind? If internal resonance shaped it, why is the structure so flawless compared to other galaxies that experience such dynamics? This is why describing Hoag's object isn't just about painting a picture of what it looks like, it's about conveying the sheer improbability of its existence. Its basic appearance tells a story that doesn't fit neatly into our current understanding of galactic evolution. And because of that, every astronomer who stares at its glowing ring is reminded of how incomplete our knowledge still is. Hoag's object doesn't just shine as a beautiful anomaly in the night sky, it stands as a challenge, a cosmic dare for humanity to dig deeper into the mechanics of the universe. What makes Hoag's object truly extraordinary is not merely its appearance but the fact that it exists at all. In the vast expanse of the observable universe, galaxies come in a few broad categories: spiral, elliptical, lenticular, and irregular. These categories, while diverse, are the result of billions of years of gravitational evolution, collisions, and star formation processes. Each type follows patterns that astronomers have learned to recognize. Spirals twist in majestic arms, ellipticals swell with the combined light of ancient stars, and irregulars scatter their stars in chaotic, unpredictable configurations. Hoag's object, however, does not fit into any of these molds. It is a phenomenon that almost seems to have been designed to defy categorization. Ring galaxies themselves are rare, but what sets Hoag's object apart is the perfection of its ring and the isolation of its core. Most ring galaxies we observe are products of dramatic interactions, usually collisions with smaller companion galaxies that send ripples of gas and stars outward, forming an irregular or asymmetric ring. These collisions often leave behind warped structures, tidal tails, or bridges of matter connecting the two galaxies. In contrast, Hoag's object is immaculate. Its blue ring forms a nearly flawless circle around a central golden core, with no visible connection to another galaxy and no tidal distortions that could hint at past violence. This structural perfection has led astronomers to regard it not just as unusual, but as an outlier of cosmic proportions. The uniqueness is further compounded when we consider the ages of the stars in the two main components. The core contains older, yellow stars, while the outer ring is composed of young, hot blue stars. This combination is unusual because it suggests two distinct phases of star formation separated by a vast, nearly empty gap. Most galaxies exhibit a mix of stars at various stages, with gradients rather than sharp divisions. Yet in Hoag's object, the separation is nearly absolute, highlighting a level of organized structure rarely seen in the universe. The very existence of a perfect central core surrounded by a completely detached ring poses questions that go beyond aesthetics and into the mechanics of galaxy formation itself. Its rarity is not just a matter of visual symmetry. Statistically, fewer than 0.1% of all observed galaxies are ring-shaped, and most of those rings are irregular or distorted. That makes Hoag's object an extreme outlier even among ring galaxies. When astronomers conduct surveys of the cosmos, they rarely encounter anything comparable. While rings can form under certain conditions, the precision and clarity of Hoag's object are almost unmatched. This makes it a critical object for study, because it represents a type of galactic structure that is extraordinarily unlikely, suggesting that there may be physical processes at work that we don't fully understand. Another aspect of its uniqueness lies in its isolation. Unlike many ring galaxies that are in the aftermath of collisions or are gravitationally tied to nearby neighbors, Hoag's object appears to exist in relative solitude. This absence of nearby companions raises further questions. If it did form from a collision, where is the intruder galaxy now? If internal dynamics created the ring, why did these forces produce such an elegant and perfectly round structure? The galaxy's apparent isolation strengthens the puzzle, making it not only beautiful but fundamentally mysterious. Its geometric precision also distinguishes it from similar objects. Astronomers often describe it as one of the most symmetrical galaxies known. While many spiral or ring galaxies show asymmetry, irregularity, or distortion due to gravitational interactions, Hoag's object maintains a circular form that is almost mathematically exact. The uniformity of the ring, the perfect spacing between the core and the ring, and the consistent brightness of the stars within the ring contribute to a sense of cosmic order rarely observed on such a scale. In a universe governed by chaotic forces, Hoag's object is an anomaly, a rare equilibrium that challenges our assumptions about what is physically possible in galactic evolution. The galaxy's uniqueness also extends to its ability to capture the imagination of both scientists and the public. Its form is visually compelling in ways that are almost unnatural, evoking comparisons to otherworldly constructs rather than natural phenomena. Many astronomers have noted that it seems almost engineered, a visual paradox that embodies both simplicity and complexity. It's a rare instance where the universe seems to produce an object that is as pleasing to the eye as it is challenging to the intellect. This combination of aesthetic perfection and scientific perplexity is part of what has cemented Hoag's object as a symbol of the mysteries of the cosmos. Furthermore, Hoag's object is unique in how it resists simple categorization within existing theoretical frameworks. When researchers attempt to explain its formation using standard models of galactic dynamics, whether through collisions, resonances, or other mechanisms, the galaxy refuses to conform neatly to predictions. Many ring galaxies exhibit residual irregularities, disrupted star clusters, or uneven gas distributions, all of which are absent in Hoag's object. Its structural integrity over hundreds of millions of light-years of scale is unprecedented, making it a critical test case for theories of galactic formation and evolution. Even beyond the physical and mathematical anomalies, Hoag's object represents a conceptual challenge. Galaxies are expected to evolve gradually, shaped by stochastic processes and interactions over cosmic timescales. Yet here is a galaxy that appears almost frozen in an idealized state, maintaining its symmetry across millions of years. It raises the possibility that some natural processes, which we have yet to fully comprehend, are capable of producing extreme order in environments that are otherwise chaotic. Hoag's object, in this sense, is a doorway to deeper questions about the universe, about the nature of cosmic symmetry, the mechanisms that govern star formation, and even the interplay of gravity on galactic scales. Ultimately, Hoag's object is a galaxy that refuses to be ordinary. It is a rare gem in the cosmic wilderness, a reminder that the universe still holds structures and phenomena that defy our expectations. Its perfect ring and isolated core, its division of old and young stars, and its defiance of conventional formation models make it not just unique, but almost otherworldly. It is a testament to the richness of the cosmos and the limits of human understanding, a single object that encapsulates both the beauty and the mystery that draw astronomers to the night sky. The story of Hoag's object begins not with its breathtaking appearance, but with the quiet, meticulous work of an astronomer peering through telescopes and sifting through photographic plates in the mid-20th century. In 1950, Arthur Hoag, a young American astronomer, was conducting routine surveys of the sky, meticulously cataloging galaxies and studying their structures. At that time, the field of extragalactic astronomy was expanding rapidly, with astronomers beginning to understand the diversity of galaxies and the ways in which they evolve. Yet even amid this burgeoning understanding, few could have anticipated encountering a galaxy as enigmatic as the one that now bears Hoag's name. Arthur Hoag was examining photographic plates taken with a wide-field telescope, a common method of the era for surveying large portions of the sky. These plates were black and white images, often grainy by modern standards, requiring careful scrutiny to identify unusual features. While inspecting the field in the constellation of Serpens, Hoag noticed something that immediately stood out: a small, bright core of light surrounded by a faint, seemingly circular halo. At first glance, it could have been mistaken for a distant planetary nebula or even a peculiar star cluster. But the separation between the central object and the outer halo hinted that this was something much more extraordinary, a galaxy unlike any he had ever encountered. Hoag's initial reaction, like that of many astronomers confronted with the unknown, was cautious curiosity. In his 1950 paper, he described the object as an apparent peculiar galaxy and noted its unusual characteristics. One of the challenges he faced was that the photographic technology of the time made it difficult to discern fine details, especially the exact nature of the surrounding ring. He observed the bright central nucleus, composed of older, yellowish stars, and saw what appeared to be a detached ring of fainter light encircling it. The stark contrast between the core and the ring was evident even on the grainy plates, and it immediately raised questions about the formation and stability of such a system. Initially, Hoag considered several possibilities. One hypothesis was that the object might be a planetary nebula, a type of glowing shell of ionized gas expelled by dying stars. However, the scale of the structure did not fit known planetary nebulae, which are vastly smaller and more diffuse. Another thought was that it could be an unusual type of barred or spiral galaxy, seen from a peculiar angle that made its arms appear as a ring. Yet even this explanation seemed insufficient, as the symmetry and isolation of the ring did not align with what was observed in other spiral systems. Ultimately, Hoag's careful measurements and observations led him to conclude that the object was indeed a galaxy, though one that defied standard classification. He noted its small angular size, estimated distances, and unusual structural composition, but he could not offer a definitive explanation for its formation. His discovery was significant not only because it revealed an entirely new type of galaxy, but also because it challenged existing theories about galactic evolution. Hoag's object was not simply another entry in a catalogue, it was a puzzle that would remain unsolved for decades. Following its initial identification, astronomers began to study the object with increasingly sophisticated instruments. Spectroscopic analysis confirmed that the core and the ring shared a similar redshift, meaning they were physically associated rather than merely a chance line-of-sight alignment. This validated Hoag's assertion that he had indeed discovered a unique type of galaxy, one with a central core and a surrounding ring that were intimately connected yet strikingly distinct. Hoag himself remained intrigued by the galaxy for many years, as did his colleagues. The discovery was initially met with a mixture of fascination and skepticism. Some wondered whether the object was a rare anomaly, a product of observational error, or even an optical illusion. But as more images were taken and technology improved, the reality of Hoag's object became undeniable. Its clear, almost sculpted appearance confirmed that it was not only real, but one of the most visually striking galaxies ever observed. The story of Arthur Hoag's discovery also highlights the broader context of astronomy in the mid-20th century. This was a period when astronomers were beginning to appreciate the diversity of galactic forms and the complexity of cosmic structures. The Hubble sequence, classifying galaxies into spirals, ellipticals, and irregulars, had been proposed just a decade earlier, and yet Hoag's object did not comfortably fit within any of these categories. It served as a reminder that the universe often resists simple classification, offering objects that challenge established theories and demand new ways of thinking. In a sense, Hoag's meticulous observations were the beginning of a long dialogue between human curiosity and the universe itself. The galaxy, with its detached blue ring and golden core, would continue to intrigue astronomers for decades, inspiring debates, theoretical models, and eventually high-resolution imaging from advanced telescopes. Arthur Hoag's discovery was more than the identification of a peculiar galaxy. It was the first chapter in a story that continues today, as scientists strive to understand how such a perfectly symmetrical, isolated structure could form in a universe governed by chaos and random gravitational interactions. At the heart of Hoag's object lies a central core that seems almost impossibly perfect. This golden-yellow sphere, seemingly suspended in a dark void, is composed primarily of old, densely packed stars, the cosmic elders of this galaxy. Unlike the young, vibrant stars in the surrounding ring, the stars in the core are long-lived, having burned for billions of years. Their yellowish hue is a natural indicator of their age. As stars exhaust the hydrogen fuel in their cores, they transition into cooler, less energetic stages, producing the warm glow characteristic of older stellar populations. In the context of Hoag's object, this core functions almost like a beacon of time, a concentrated cluster of cosmic history encased within the young, energetic ring surrounding it. The density of the core is another striking feature. Unlike the ring, which is spread out and composed of scattered clusters of blue stars, the central core is tightly packed, creating a gravitational anchor that holds the galaxy together. Its compactness suggests a significant concentration of mass, which in turn influences the dynamics of the ring. The gravitational pull of the core likely played a key role in shaping the surrounding stars, either by stabilizing them into orbit or by contributing to the formation of the gap that separates the core from the outer ring. The sheer density also implies that this central region has been relatively undisturbed over billions of years, preserving its structure in a universe where most galaxies undergo constant change and occasional chaos from collisions or mergers. Visually, the core presents a stark and almost poetic contrast with the outer ring. The warm, muted yellow glow of the core conveys a sense of age, stability, and endurance, while the vibrant blue ring represents youth, activity, and formation. This juxtaposition creates a dramatic visual and scientific statement. Within a single galaxy, we see two extremely different stellar populations coexisting in perfect separation. Astronomers refer to this as a bimodal distribution of stars, and while it is not unique in principle, the clarity and isolation in Hoag's object are extraordinary. In most galaxies, older stars are mixed with younger populations, forming gradients that transition gradually rather than separating cleanly. Hoag's object defies this pattern, preserving a pristine separation that has become one of its most puzzling features. The formation of the core itself raises intriguing questions. Its age and density suggest it could be the remnant of an early galactic nucleus, a relic from the galaxy's initial formation period. Some researchers speculate that it may have been a fully formed elliptical galaxy at some point, later enveloped by the material that eventually became the ring. Others propose that the core and the ring formed through different processes entirely, with the ring representing a subsequent wave of star formation triggered by an as-yet unidentified event. Regardless of its origin, the core stands as a testament to the longevity and resilience of stellar systems, surviving through billions of years of cosmic evolution while maintaining structural perfection. The stellar population within the core also provides clues to astronomers about the chemical evolution of Hoag's object. Older stars like these typically contain heavier elements synthesized over many generations of supernovae, offering insight into the enrichment of the galaxy's interstellar medium. In contrast, the younger stars in the ring are formed from more recently accumulated gas, often less enriched by heavy elements, though still influenced by the metallicity of the surrounding environment. This chemical contrast mirrors the visual one, reinforcing the idea of two distinct stellar environments coexisting within a single galactic system. Furthermore, the core's gravitational influence cannot be understated. It likely governs the orbital dynamics of the ring, keeping the blue stars in their near-perfect circular path and maintaining the separation between the inner and outer regions. Some theories propose that without such a dense central mass, the ring would not have formed so symmetrically, and the gap between core and ring would not have remained so clear. The core acts as a stabilizing force, a silent regulator that ensures the galaxy's striking geometry persists over cosmic timescales. From an observational standpoint, the core's clarity and isolation make Hoag's object stand out among other ring galaxies. In many other systems, the central region is messy, obscured by dust or disrupted by gravitational interactions. Here, the golden nucleus shines unobstructed, allowing astronomers to study its structure in detail. High-resolution imaging has revealed a smooth, spheroidal distribution of stars, emphasizing its age and stability, while spectroscopic studies confirm that it is composed of older, evolved stars, consistent with theories of galactic evolution but unusual in its apparent pristine condition. The contrast between the core and the ring is not only a visual delight but also a critical clue in understanding the galaxy's origin. Any theory attempting to explain Hoag's object must account for this separation, the existence of an old, dense core that is entirely distinct from the young, outer ring. It is one of the reasons why theories like simple collision models or resonance-based explanations face challenges. While such processes can create rings, reproducing a perfect coring separation with such clarity is far more difficult. The central nucleus of Hoag's object, therefore, is not just a feature. It is a key piece of the puzzle, a stable anchor around which the rest of the galaxy orbits, both physically and conceptually. Encircling the golden heart of Hoag's object is the feature that has captivated astronomers and stargazers alike, its luminous, nearly perfect outer ring. This ring is composed predominantly of young, massive, and hot blue stars, each radiating tremendous energy and light. Their color immediately signals their youth. In stellar astrophysics, blue stars burn hotter and faster than their older yellow or red counterparts. These stars are the vibrant, energetic youth of Hoag's object, forming a dazzling contrast to the mature, mellow glow of the central core. The first thing that strikes anyone examining the ring is its precision. Unlike many other ring galaxies, which often display asymmetry, irregular clumping, or distortions caused by collisions or gravitational interactions, Hoag's object exhibits a ring that is astonishingly circular. The stars within it are distributed with remarkable uniformity, producing a continuous band of blue light that seems almost artificially sculpted. The width of the ring is consistent along its circumference, and its separation from the central core is distinct and unbroken. Such geometric perfection in a natural object of this size is exceedingly rare, making Hoag's object one of the most visually striking examples of a ring galaxy in the observable universe. The formation of the blue stars within the ring also provides critical insights into the galaxy's history. These stars are relatively young, perhaps only tens or hundreds of millions of years old, compared to the billion-year age of the stars in the core. Their presence indicates a relatively recent period of star formation, triggered by processes that are still under scientific investigation. The ring itself may have originated from a burst of star formation fueled by gas either ejected from the central region or swept into orbit through gravitational effects. Whatever the mechanism, it resulted in a continuous, bright circle of stars that maintains its shape with an almost mechanical precision. The physical separation between the core and the ring adds to the sense of otherworldly perfection. The nearly empty gap between the two regions, often referred to as the void, is devoid of significant star clusters, dust lanes, or gas clouds that might typically obscure the symmetry of the ring. This gap emphasizes the core's isolation and enhances the visual drama of the galaxy, making the ring appear as if it is floating independently around a central golden sphere. The contrast between the dense, aged stars of the core and the sparse, young, hot stars of the ring is not just visually striking, it also poses a deep astrophysical question. What natural process could have orchestrated such a clear separation of stellar populations? The blue stars themselves are enormous compared to the Sun, burning with a brilliance that is orders of magnitude greater. These massive stars have relatively short lifespans, often only a few million years, which suggests that the ring is not a relic of ancient cosmic history but a site of ongoing or recent stellar activity. The presence of these young stars hints at reservoirs of gas in the ring, likely primordial hydrogen that has collapsed under gravity to form new stellar generations. Their high temperature and luminosity contribute to the vivid azure hue that makes the ring so visually arresting, giving it an almost neon-like glow against the darkness of space. In addition to the stars themselves, astronomers have observed that the ring may contain clusters of star-forming regions, small pockets where gas density is high enough to ignite further stellar birth. These regions are scattered along the circumference, but the overall uniformity of the ring's light suggests that star formation has occurred relatively evenly, rather than being concentrated in one sector. This even distribution adds to the sense of cosmic order, as though the stars have been carefully placed along the orbital path, producing a ring that is both dynamic and harmonious. From a gravitational perspective, the ring's stability is remarkable. In most galaxies, rings are transient structures, often disrupted over time by tidal forces, collisions with satellite galaxies, or internal instabilities. Yet the ring of Hoag's object has maintained its structure over hundreds of millions of years, orbiting the core in a nearly circular path. This stability implies a finely tuned balance between the gravitational pull of the central nucleus and the orbital momentum of the stars in the ring. The result is a configuration that appears to defy the chaotic tendencies of galactic evolution, preserving its near-perfect circular shape across enormous cosmic distances. The visual effect of the ring, when seen in high-resolution images from modern telescopes, is mesmerizing. It forms a continuous, glowing halo, sharply contrasted against the dark void separating it from the core. The azure glow seems almost surreal, as if the galaxy has been painted with a brush of pure light. Astronomers often describe it as a cosmic jewel, not only because of its color but also because of the striking geometry and clarity of the ring. Its aesthetic perfection is unparalleled among ring galaxies, which are usually irregular or warped due to their violent formation histories. The existence of this ring, composed entirely of hot, young stars, also challenges existing theories of galaxy formation. While collision and resonance models can explain the presence of rings in some galaxies, few can account for the degree of symmetry, the sharp gap from the core, and the uniformity of the stellar distribution seen here. The blue ring is not only a testament to ongoing star formation but also a living clue, a visible record of processes that astronomers are still striving to fully understand. Its regularity suggests either a rare, finely balanced event or a phenomenon entirely unique to this galaxy. Furthermore, the ring enhances the galaxy's visual and scientific allure by creating a duality: the coexistence of old and young, stable and dynamic, compact and expansive. The core and the ring are linked not by a continuous gradient of stars, as in most galaxies, but by a dramatic, almost cinematic separation. This dual structure makes Hoag's object an ideal laboratory for studying stellar populations in isolation, allowing astronomers to examine the characteristics of old stars in the core and young stars in the ring without interference from overlapping populations, as is common in other galaxies. Ultimately, the ring of Hoag's object is a phenomenon of both aesthetic wonder and scientific mystery. Its nearly perfect circularity, vibrant blue color, and clear distinction from the older central core combine to create one of the most remarkable and enigmatic structures ever observed in the universe. The outer ring is not just a collection of stars, it is a cosmic signature, a visual testament to the galaxy's unusual history, and a persistent challenge to our understanding of how galaxies can form and evolve under the laws of physics as we know them. Its perfection invites study, speculation, and admiration, reinforcing why Hoag's object continues to captivate astronomers and the public alike, decades after its discovery. Hoag's object is not only visually extraordinary, it is statistically exceptional, a genuine outlier in the cosmic population of galaxies. To appreciate its rarity, it helps to understand the vast diversity and sheer numbers of galaxies that populate the observable universe. Astronomers estimate that there are at least 100 to 200 billion galaxies within the observable cosmos, ranging from tiny dwarf galaxies to colossal ellipticals containing trillions of stars. Each galaxy has been shaped over billions of years by gravitational interactions, star formation, and, often, cosmic collisions. Most follow predictable patterns: spirals, ellipticals, lenticulus, or irregulars. Even among ring galaxies, which are themselves a rare category, structures like Hoag's object are exceedingly uncommon. Ring galaxies account for fewer than 0.1% of all observed galaxies, and the majority of these are not the elegant, perfectly symmetric systems seen in Hoag's object. Typically, ring galaxies form as the result of galactic collisions or interactions, which create outward propagating density waves that trigger bursts of star formation in a circular pattern. In these cases, the rings are often irregular, warped, or incomplete, and frequently accompanied by distortions in the core or surrounding regions. Even within this already rare group, Hoag's object stands apart because of its isolation, symmetry, and the clear separation of its old core from the young outer ring. To put this into perspective, imagine surveying 1,000,000 galaxies. Fewer than 1,000 of them would even qualify as ring galaxies. Among those 1,000, perhaps a handful would exhibit any form of symmetry approaching that of Hoag's object. In other words, the odds of encountering a galaxy like this are astronomically small. Its rarity is not merely a matter of aesthetic interest, it also makes the galaxy a critical subject for scientific research. The fact that it exists at all challenges conventional models of galactic formation and evolution. Scientists must ask themselves, how could such a pristine and isolated structure form in a universe dominated by random motions, collisions, and gravitational perturbations? Even within the category of ring galaxies, most examples are imperfect. Consider the well-known Cartwheel Galaxy, another ring galaxy created by a dramatic collision with a smaller intruder. The Cartwheel displays a prominent outer ring, but it is irregular, with spokes and distortions radiating inward and outward from the center. Its core is not as clearly defined, and its ring shows uneven star formation along its circumference. By contrast, Hoag's object has a core and ring that are perfectly separated and geometrically flawless, which makes it an extreme outlier, even when compared to other ring galaxies. The rarity of Hoag's object is further emphasized by its apparent isolation. Many other ring galaxies are either interacting with neighboring galaxies or show evidence of tidal disturbances. Such interactions are almost always necessary in models that produce ring structures, because creating a circular burst of star formation generally requires an external perturbation. Yet Hoag's object floats alone in its local environment, with no obvious nearby galaxy that could have caused its formation through gravitational collision. This level of isolation combined with near-perfect symmetry is extremely rare, perhaps unique among the galaxies we have observed with modern telescopes. From a statistical standpoint, Hoag's object exemplifies what astronomers call an extreme outlier, a system that sits at the very edge of possible galactic configurations. While galaxies are diverse, they tend to cluster around certain structural norms, with spirals and ellipticals dominating the population. The fraction of galaxies that deviate significantly from these norms is small. Ring galaxies themselves are rare, perfectly symmetric, isolated ones are even rarer. Hoag's object occupies an extreme position in the tail of the distribution of galactic forms, a 1 in billions configuration that seems almost intentionally designed to challenge our understanding of the cosmos. The galaxy's rarity is not just a statistical curiosity, it has profound implications for astrophysics. Because Hoag's object is so unusual, it provides a unique laboratory for testing models of star formation, galactic dynamics, and gravitational stability. In most galaxies, overlapping stellar populations, dust lanes, and irregular structures make it difficult to isolate the effects of specific physical processes. Hoag's object, with its clearly defined core, empty gap, and uniform ring, allows astronomers to study these processes in a controlled, almost idealized environment. Its rarity thus enhances its scientific value. While we may observe millions of galaxies, few present the clear, isolated conditions needed to investigate the fundamental principles that govern galactic evolution. Moreover, the rarity of Hoag's object fuels both fascination and speculation. Could it be a product of some extremely rare cosmic accident, a collision that occurred under near-perfect conditions? Or does it represent a type of galactic formation that occurs more often than we realize but is difficult to detect because of observational limitations? Some astronomers suggest that we may be missing other galaxies like Hoag's object simply because they are faint, distant, or oriented in ways that make their rings difficult to observe. Nonetheless, even considering these possibilities, the galaxy remains one of the most extreme examples of symmetry and structural isolation in the known universe. Its uniqueness also shapes the way astronomers think about galactic classification. While the Hubble sequence provides a framework for categorizing the vast majority of galaxies, Hoag's object defies easy placement. It does not fit neatly into spiral, elliptical, or irregular categories, and its ring cannot be classified simply as a tidal feature without stretching conventional definitions. This rarity highlights the limitations of our classification systems and reminds us that nature is not constrained by human-imposed categories. Galaxies like Hoag's object exist on the fringes, pushing the boundaries of our understanding and demonstrating that the universe is far more diverse and surprising than even our most sophisticated models might predict. In short, Hoag's object is rare not only in appearance but in its physical and structural properties. Its near-perfect ring, its isolated core, and its clarity of separation between old and young stellar populations make it a cosmic anomaly. While ring galaxies exist in the universe, few approach the visual and structural precision of this extraordinary object. It is a striking reminder that even in a universe filled with billions of galaxies, some are so unusual, so extreme, that they stand as solitary testaments to the complexity and mystery of cosmic evolution. In the grand tapestry of the cosmos, Hoag's object is a glittering thread of exception, a galaxy that is not merely rare, but almost unique. Despite decades of observation, imaging, and theoretical modeling, Hoag's object remains one of the universe's most compelling unsolved mysteries. While astronomers can describe its features, the golden yellow core, the luminous blue ring, and the nearly perfect separation between the two, they still cannot definitively explain how such a clean and symmetrical structure formed. Unlike many other galaxies, whose origins and evolution can be traced through collisions, mergers, or internal dynamics, Hoag's object defies conventional explanations, leaving scientists both fascinated and frustrated. The first and most immediate question concerns the origin of the ring itself. In most galaxies, rings are the product of violent events. A smaller galaxy colliding with a larger one, density waves propagating through a galactic disk, or resonances induced by internal gravitational forces. Each of these processes typically leaves behind irregularities, warps, clumps, tidal debris, or uneven star distributions. Hoag's object, by contrast, exhibits a ring of near-perfect circularity, with uniform star formation along its circumference and no visible distortions or interruptions. The precision of this structure makes it extraordinarily difficult to reconcile with theories of chaotic galactic evolution. How could such a symmetrical ring emerge in a universe where collisions are messy, gravity is unpredictable, and cosmic material rarely arranges itself with such mathematical clarity? Astronomers also struggle to explain the gap between the core and the ring, an area largely devoid of stars, gas, or dust. In typical ring galaxies formed by collisions, the inner regions are often partially filled with residual matter, and the boundaries between core and ring are fuzzy. In Hoag's object, however, the core appears completely isolated, with the ring orbiting at a distance that maintains a near-perfect void. This separation is not just a visual anomaly, it is a dynamical puzzle. The gravitational forces from the core should influence material in the surrounding space, yet the gap has remained stable over immense cosmic timescales. Why hasn't matter filled in this void? Or why hasn't the ring migrated inward due to gravitational interactions? Current models struggle to account for this enduring isolation. Another unresolved question concerns the coexistence of two distinct stellar populations. The core is composed of older, yellow stars, while the ring is dominated by hot, blue stars. This sharp division implies at least two separate epochs of star formation, an ancient, early generation for the core, and a much younger, more recent burst for the ring. Yet the mechanisms that could produce such distinct separation are unclear. Did the core form first as a standalone galaxy and somehow trigger the formation of the ring later? Or did some external event selectively compress gas into a ring without disturbing the older central stars? The absence of definitive evidence for either scenario underscores how little we truly understand about the processes at play in this galaxy. Adding to the uncertainty is the galaxy's apparent isolation. Many ring galaxies are the product of interactions with neighboring galaxies, yet Hoag's object appears to float alone, with no obvious companion or intruder visible. If a collision occurred in its past, where is the other galaxy? Where is the tidal debris that would normally accompany such an event? Its solitude deepens the mystery, forcing astronomers to consider alternative explanations that go beyond the standard frameworks for ring formation. Hoag's object also challenges our understanding of gravitational dynamics on galactic scales. In most galaxies, deviations from symmetry are expected because of internal instabilities, dark matter distribution, and the influence of nearby celestial bodies. The near-perfect circularity and stability of Hoag's object suggest a finely balanced set of forces, yet how such equilibrium could be naturally achieved and maintained over billions of years is unknown. Are there subtle gravitational mechanisms at work that we have yet to observe? Could there be physical processes beyond our current understanding of galaxy formation? The chemical composition of the galaxy adds further uncertainty. The older stars in the core contain heavier elements, products of multiple generations of stellar evolution, while the blue stars in the ring are relatively young and energetic. This dichotomy implies that star formation in the ring was fueled by gas that either avoided enrichment from the older population or was introduced separately. How this material ended up forming a smooth, continuous ring rather than dispersing chaotically remains an open question. Modern telescopes, including the Hubble Space Telescope, have provided high-resolution images that reveal the extraordinary symmetry and clarity of the ring, but they have not provided definitive answers regarding the galaxy's formation. Spectroscopy and other observational techniques confirm the age difference between the core and the ring, yet the exact mechanism that produced the gap, the perfect circularity, and the structural stability remains elusive. Even advanced computer simulations struggle to recreate a galaxy with Hoag's object's exact characteristics without resorting to improbable or finely tuned scenarios. Ultimately, what we don't know about Hoag's object is profound. It is not just a question of missing data. It is a question of fundamental understanding. This galaxy exposes the limits of our current models of galactic evolution, star formation, and gravitational dynamics. It stands as a reminder that despite decades of astronomical research, the universe can still produce structures that resist explanation, challenging our assumptions and inspiring new lines of inquiry. The mystery of Hoag's object is compounded by its enduring perfection. While most unusual galaxies can be dismissed as products of random cosmic events or messy collisions, this galaxy's elegance suggests that there may be processes in the universe that are capable of producing extreme order on a massive scale. It asks questions that go beyond the formation of a single galaxy. Could there be physical laws, resonances, or cosmic conditions that we have yet to recognize, capable of sculpting matter into forms of near-perfect symmetry? In short, Hoag's object represents a cosmic puzzle that remains unsolved. Every aspect of its structure, the pristine core, the uniform blue ring, the empty gap, and the isolated environment, raises questions that astronomers are still grappling with. Despite decades of observation, it continues to defy full explanation, reminding us that the universe is far more complex, subtle, and astonishing than our current theories can account for. It is a galaxy that challenges not only our understanding of cosmic processes but also our sense of possibility, standing as a monument to the unknown, a silent enigma orbiting quietly in the depths of space. One of the earliest and most widely considered explanations for Hoag's object's striking ring is the collision theory. According to this idea, the galaxy's nearly perfect outer ring of young blue stars may have formed as the result of a dramatic, head-on encounter with a smaller galaxy. In essence, this hypothesis treats Hoag's object not as a purely isolated system, but as a cosmic accident, an event in which gravity, motion, and stellar material aligned in such a rare and precise way that it produced the extraordinary geometry we observe today. The underlying mechanics of the collision theory are rooted in what astronomers call a bullseye collision or ring-making interaction. In a simplified version, imagine a smaller galaxy moving directly along the axis of a larger, more massive galaxy, passing through its center. The gravitational shock from the intruder's passage compresses the gas in the larger galaxy, sending it outward in a ripple or wave. As this wave propagates through the galactic disk, it triggers intense bursts of star formation, forming a ring of young, hot stars. This process has been observed in other galaxies, most famously in the Cartwheel Galaxy, which shows an irregular but visually distinct ring caused by a collision with a smaller companion galaxy. Applied to Hoag's object, The theory suggests that a smaller intruder galaxy may have plunged through the original core, compressing the surrounding gas into a circular wave that eventually formed the luminous blue ring we see today. The outer ring, therefore, would be a direct result of the energy imparted by the collision, with the young stars representing newly formed material ignited by the sudden increase in pressure. The empty gap between the core and the ring could also be explained by this mechanism. As the wave expanded outward, it cleared the inner region of gas and dust, leaving the central core largely untouched while concentrating star formation at a specific radius. There is some evidence supporting this idea. Ring galaxies are known to form through collisions, and the physics of density waves and shock propagation can produce circular patterns of star formation. The morphology of Hoag's object, a bright central core surrounded by a ring, fits, at least superficially, the expected outcome of such an event. Furthermore, the presence of young blue stars in the ring is consistent with a relatively recent burst of star formation, which aligns with the timescales expected following a galactic collision. However, applying the collision theory to Hoag's object presents significant challenges. In most collision-formed ring galaxies, astronomers observe telltale signs of disruption: tidal tails, streams of stars pulled outward, irregularities in the ring, or remnants of the intruding galaxy. Hoag's object, by contrast, displays none of these features. The ring is extraordinarily uniform, the core is unperturbed, and no obvious remnant of the supposed intruder galaxy can be found in its immediate vicinity. The absence of these expected scars raises doubts about whether a collision alone could have produced the galaxy's current form. Timing also complicates the collision theory. For the outer ring stars to be as young as they appear, the collision would need to have occurred relatively recently in cosmic terms, perhaps only a few 100 million years ago. Yet if such a significant event had occurred, one might expect the central core to show signs of disturbance, at least in the form of gas inflows, star formation, or structural deformation. The fact that the core appears stable and unscathed further complicates the theory. Another issue is the galaxy's isolation. Most collisions occur within galaxy clusters or environments where multiple galaxies are in proximity, increasing the likelihood of encounters. Hoag's object, however, exists in a relatively sparse neighborhood. No suitable candidate for a former intruder galaxy has been identified nearby, and searches for tidal debris or stellar remnants have come up largely empty. This makes the scenario of a perfectly aligned head-on collision highly improbable, though not impossible. Astronomers must consider the statistical rarity of such an event when evaluating this theory. Despite these challenges, the collision theory remains appealing because it can, in principle, explain the separation of the old core from the young ring and the intense burst of star formation in the ring. In simulations, head-on collisions can produce circular waves that lead to ring formation, providing a plausible mechanism for the existence of the blue stellar population. The difficulty lies in reconciling the theory with the observed perfection of the ring and the lack of disturbances elsewhere in the galaxy. In summary, the collision theory frames Hoag's object as the result of a rare, precise cosmic event, a smaller galaxy passing directly through the center of a larger one, generating a ring of star formation while leaving the core intact. It is a physically plausible explanation for the formation of the blue ring, and it aligns with known processes in other ring galaxies. Yet the lack of observational evidence for an intruder, the galaxy's extreme symmetry, and the pristine nature of both the core and the ring suggest that this theory cannot fully account for all of Hoag's object's unusual features. While collision theory provides an important framework, it is not a complete answer, leaving room for alternative hypotheses that might better explain the galaxy's unique geometry. An alternative explanation for the striking structure of Hoag's object is the gravitational resonance theory, which proposes that its near-perfect ring was formed not by an external collision, but through internal gravitational dynamics. In this model, the galaxy's own mass distribution, rotation, and the interplay of gravitational forces within the system could have caused gas and stars to migrate outward, coalescing into a sharply defined ring around the central core. Unlike the collision theory, which relies on a rare cosmic event, gravitational resonance focuses on the intrinsic mechanics of the galaxy itself. Gravitational resonance occurs when orbital motions of stars and gas clouds in a galaxy synchronize in such a way that material accumulates at certain stable distances from the galactic center. Essentially, the gravitational potential of the core and the surrounding galaxy can create regions of stability where matter naturally collects. Over millions of years, gas in these resonant regions can condense, collapse, and form new stars, resulting in a ring-like distribution. In the case of Hoag's object, the gravitational pull of the dense, old core may have established a resonance zone at a specific radius, where the young, hot blue stars eventually formed the luminous outer ring we observe today. One of the attractive aspects of the gravitational resonance theory is that it can account for the clean separation between the core and the ring. The inner gap, the void between the yellow core and the blue ring, could represent a region where gravitational forces are unfavorable for star formation. Gas and dust might have been either depleted or prevented from collapsing into stars within this zone due to the orbital dynamics dictated by the resonance. This provides a natural explanation for why Hoag's object maintains such an empty moat, something that the collision theory struggles to justify without invoking highly improbable circumstances. Resonance theory also aligns with observations of other galaxies where internal dynamics produce ring-like features, though usually on a smaller or less perfect scale. For example, barred spiral galaxies sometimes exhibit inner or outer rings created by orbital resonances between the bar's rotation and the surrounding disk. These rings, known as Lindblad resonances, occur at radii where gravitational forces and orbital periods synchronize, causing gas to accumulate and form new stars. Gravitational resonance in Hoag's object could represent a similar process, scaled up dramatically to produce a nearly flawless circular ring around an isolated core. Another advantage of this theory is that it does not require the presence of an external galaxy or collision event. Hoag's object is remarkably isolated, and no intruding galaxy or tidal debris has been observed nearby. Internal gravitational processes could therefore provide a self-contained explanation for the ring's formation, consistent with the galaxy's solitary environment. This eliminates some of the improbabilities associated with collision theory, such as requiring a head-on encounter that aligns perfectly to create a symmetric ring without leaving observable remnants. However, there are challenges with the gravitational resonance explanation as well. For one, most resonance-induced rings in other galaxies are less uniform and often show signs of distortion or irregularity due to the complex interplay of forces within the galactic disk. Reproducing the extreme symmetry and smoothness of Hoag's objects ring through resonance alone is difficult. The theory must account not only for the ring's circularity but also for the clear demarcation between the old core and the young ring, and for the uniformity of star formation across the circumference. Simulations suggest that producing such a perfect structure would require highly specific initial conditions in the galaxy's mass distribution and rotational profile, conditions that may themselves be rare. Another challenge lies in explaining the origin of the material that forms the ring. Resonance theory requires a sufficient reservoir of gas at the correct radius to collapse into stars, and the dynamics must remain stable long enough for star formation to occur evenly around the orbit. The presence of such a pristine, massive reservoir without it dispersing or forming stars at irregular locations is difficult to reconcile with standard models of galactic evolution. It implies a level of internal stability that is uncommon for most galaxies, further highlighting the unusual nature of Hoag's object. Despite these difficulties, gravitational resonance theory is compelling because it provides a mechanism that relies purely on the physics of the galaxy itself, rather than improbable external events. It offers a plausible pathway for the emergence of Hoag's object's unique geometry, linking the core's mass and the orbital dynamics of the surrounding gas to the formation of the ring. By focusing on how internal forces might sculpt matter over billions of years, this model aligns with the galaxy's isolation and its symmetrical perfection, offering a complementary perspective to collision-based hypotheses. Ultimately, the gravitational resonance theory underscores the complexity of Hoag's object and the challenges of explaining it fully. While it accounts for some features, the uniform ring, the empty gap, and the absence of an obvious intruder, it does not entirely solve the puzzle, particularly in reproducing the galaxy's extraordinary symmetry and structural perfection. Like collision theory, it provides a framework for understanding part of the phenomenon but leaves unanswered questions, demonstrating that Hoag's object continues to challenge even our most sophisticated models of galactic formation. Neither the collision theory nor the gravitational resonance theory can fully account for all the peculiarities of Hoag's object, and this is precisely what makes the galaxy so enigmatic. Each explanation addresses certain aspects of its structure, but both fall short in reproducing the extraordinary symmetry, isolation, and separation of stellar populations that define the galaxy. Examining the limitations of these models illuminates just how anomalous Hoag's object truly is. Starting with the collision theory, the idea that a smaller galaxy passed directly through the center of a larger system to create the outer ring does explain some features, such as the presence of the young, blue stars in the ring and the gap separating it from the older core. Collisions are known to trigger bursts of star formation, and a head-on impact can, in principle, produce a circular density wave capable of forming a ring. However, several critical problems emerge when this theory is applied to Hoag's object. First, most ring galaxies formed via collision display irregularities, including warps, spokes, tidal tails, and other distortions. Hoag's object, by contrast, exhibits a perfectly circular ring, a smooth, unbroken gap, and an undisturbed central core, conditions that are exceedingly unlikely in the aftermath of a collision. Another issue is the absence of the intruder galaxy. In almost every observed collision-induced ring, the interacting galaxy is still detectable or leaves behind remnants of tidal debris. Astronomers have searched the vicinity of Hoag's object and found no obvious candidate for a past collision, nor is there any visible tidal material or disrupted stellar structures. For a galaxy so isolated, a perfectly aligned collision would have to be extraordinarily improbable, both in timing and in trajectory. Statistically, such an event is nearly impossible, raising doubts about whether collision alone can explain the galaxy's pristine form. Additionally, the timing of the star formation presents a challenge. The blue stars in the outer ring are relatively young, but the core is ancient and undisturbed. If a collision had triggered the ring's formation, one might expect at least some evidence of secondary star formation in the central region, or signs of gravitational disturbance in the core. The core's stability contradicts the kind of violent interaction that collision theory requires, leaving a glaring inconsistency in the model. Turning to the gravitational resonance theory, this model sidesteps the need for a collision by invoking internal galactic forces. It posits that the interaction between the core's gravity, the galaxy's mass distribution, and the orbital motion of gas could naturally concentrate material into a circular ring at a specific resonance radius. This mechanism could explain the ring's uniformity and the empty gap between core and ring, which are difficult to reconcile with a collision scenario. However, gravitational resonance has its own set of problems. One major challenge is the extreme perfection of the ring. Even in simulations, internal gravitational forces tend to produce rings that are imperfect, uneven, clumpy, or elongated due to slight instabilities in the disk. Achieving the near-perfect symmetry seen in Hoag's object would require extraordinarily precise initial conditions, including an unusually smooth mass distribution and an almost perfectly balanced rotational profile. While not impossible, such conditions are statistically rare, raising the question of whether resonance alone is sufficient to explain the galaxy's remarkable geometry. Moreover, resonance theory struggles to account for the sharp distinction between old and young stellar populations. While internal dynamics can move gas into specific orbits, they do not naturally explain why the central core remains composed entirely of older stars while the ring is filled exclusively with young, blue stars. In most galaxies with resonance-induced rings, there is some overlap of stellar populations, or the core shows signs of ongoing star formation influenced by the redistributed gas. Hoag's object, however, maintains a nearly absolute separation, which is not easily replicated in resonance-based models. In both cases, a common problem is the pristine nature of the galaxy. Real galaxies are messy. Gravitational perturbations, minor mergers, dark matter distributions, and random gas motions tend to distort structures over millions of years. Yet Hoag's object appears untouched by these effects. Its circularity, uniformity, and stability over cosmic timescales suggest that neither a chaotic collision nor internal resonance fully accounts for the observed perfection. There seems to be a combination of forces, or perhaps unknown mechanisms, at play that have maintained this equilibrium in a way that challenges standard astrophysical models. Another complicating factor is the galaxy's isolation. Both theories face difficulties in explaining why Hoag's object exists in such solitude. Collisions are more likely in densely populated galactic neighborhoods, and resonances typically require a significant and carefully balanced mass distribution. Yet the galaxy seems relatively alone, and its surrounding environment provides no clues as to how these processes might have occurred. This isolation makes both theories less convincing as comprehensive explanations, suggesting that the full story may involve a combination of mechanisms, or something entirely unexpected. Finally, both theories also struggle to account for the timing and age distribution of stars. The outer ring's blue stars indicate relatively recent formation, while the central core consists of ancient stars. Any plausible model must explain not only the ring's formation but also why the core remained undisturbed over billions of years, and why the gap between the core and ring has persisted without filling in. Neither collision nor resonance models can fully reconcile these temporal and structural constraints without invoking highly specific and improbable conditions. In conclusion, Hoag's object resists full explanation. Collision theory provides a mechanism for ring formation but fails to account for the galaxy's symmetry, the undisturbed core, and the lack of an intruder. Gravitational resonance theory explains some aspects of internal structure and gap formation, but struggles to reproduce the flawless circularity and the absolute separation of stellar populations. Together, these shortcomings reveal the fundamental mystery. Hoag's object does not neatly align with any single formation model known to astronomers. It remains a cosmic anomaly, a challenge that continues to push the boundaries of our understanding of galactic evolution and the dynamics of the universe. To truly grasp the wonder of Hoag's object, it helps to step back and consider its scale. This is a galaxy so vast that its dimensions and distance from Earth stretch the imagination, reinforcing both its cosmic significance and the challenge it presents to astronomers. Located approximately 600 million light-years away in the constellation of Serpens, Hoag's object is far beyond the reach of our most basic observational tools, requiring high-powered telescopes to discern its intricate structure. To put that distance in perspective, the light we see from this galaxy today began its journey toward Earth 600 million years ago, long before humans even walked the planet in their modern form. What we observe is a window into the distant past, a snapshot of a galaxy frozen in time as it appeared during the late Precambrian era on Earth, when life was only beginning to flourish in the oceans. Its sheer size is equally staggering. Hoag's object spans nearly 100,000 light-years in diameter, roughly comparable to the size of our own Milky Way galaxy. To imagine this scale, consider that light, traveling at 186,282 miles per second, would take 100,000 years to traverse the galaxy from edge to edge. Even the distance across its luminous outer ring is immense, containing billions of stars arranged in a perfect circle, each separated by tens or hundreds of light-years from its neighbors. The central core itself, a dense sphere of older yellow stars, is likely tens of thousands of light-years across, containing enough mass to exert a significant gravitational pull on the surrounding ring. In other words, we are looking at a system of colossal proportions, yet one that is arranged with a precision and symmetry that seems almost microscopic in its attention to detail, considering the vast distances involved. When considering these numbers, it becomes easier to appreciate just how extraordinary the geometry of Hoag's object is. Creating a nearly perfect circular ring across a span of 100,000 light-years requires a level of order and stability that is almost inconceivable. Small deviations in gravitational forces, star formation rates, or orbital velocities could distort the ring beyond recognition, yet it persists in remarkable uniformity. The scale amplifies the mystery. It is not a small, controlled laboratory experiment. It is a massive, multi-billion star system maintaining structural perfection over hundreds of millions of years. From an observational standpoint, the galaxy's distance also explains why it took decades for astronomers to study it in detail. At 600 million light-years away, Hoag's object is faint and small on the sky compared to nearer galaxies, making it difficult to resolve its structure without advanced telescopes. Even today, only instruments like the Hubble Space Telescope or large ground-based observatories equipped with adaptive optics can capture images detailed enough to reveal the clear separation between core and ring. Before the advent of modern astrophotography, such a galaxy might have appeared as nothing more than a faint, circular smudge, its extraordinary symmetry invisible to early astronomers. The scale of Hoag's object also emphasizes the staggering amount of material involved in its formation. The core alone likely contains billions of stars, while the ring, composed of hot, blue stars, is also home to countless stellar systems. Gas clouds, stellar remnants, and dark matter, though invisible, would extend across both regions, influencing the galaxy's dynamics and gravitational stability. Coordinating the motion of all this material to form a nearly perfect ring over tens of thousands of light-years is a feat that challenges conventional models of galactic evolution. It is not just the arrangement of stars that is remarkable. It is the orchestration of matter across unimaginable distances and timescales. Considering the galaxy's distance and size also gives perspective on the timescales involved in its evolution. Light traveling from the outer ring takes hundreds of thousands of years to reach the core, and millions of years for the ring to complete a single orbit around the nucleus. The processes that formed the ring, whether collision, resonance, or some unknown mechanism, unfolded over millions or even billions of years. The galaxy's age and scale remind us that cosmic events operate on timeframes far beyond human experience, yet produce patterns of astonishing symmetry and beauty. In popular terms, imagine trying to create a perfect circle on a canvas 100,000 light-years across, with billions of points of light, while simultaneously balancing the gravitational forces of a dense central sphere. The difficulty of this task underscores why Hoag's object continues to baffle astronomers. Its scale transforms the mystery from a curiosity of morphology into a profound question about the fundamental processes that govern the universe. How can matter behave with such precision over distances and timescales that are almost incomprehensible? The immense scale also accentuates the galaxy's place in the broader universe. At 600 million light-years away, it is far beyond our local group of galaxies, situated in a region of the cosmos that has remained relatively undisturbed by nearby massive galaxies. Its isolation, coupled with its enormous size, reinforces the impression of Hoag's object as a cosmic gem, floating in relative solitude, a massive system maintaining an extraordinary degree of order in a universe that is often chaotic and dynamic. Ultimately, appreciating the scale of Hoag's object adds a layer of wonder to its already enigmatic nature. It is a structure of almost unimaginable dimensions, visible to us only as a faint glimmer, yet exhibiting a degree of symmetry and clarity that is truly rare in the cosmos. Its distance and size remind us that we are peering not just across space but across time, observing a galaxy that challenges our understanding of physics, star formation, and galactic evolution on an epic scale. Hoag's object is not just a visually stunning object, it is a monument to the immensity and complexity of the universe, a structure whose scale amplifies the mystery it represents. Adding to the surreal and almost otherworldly nature of Hoag's object is a detail that often goes unnoticed but adds layers of intrigue to its cosmic story. A second ring galaxy can be seen through the outer ring of Hoag's object, appearing as a faint, ghostly circle in the distant background. This secondary ring is not physically associated with Hoag's object. Rather, it lies much farther away, aligned along our line of sight in a way that creates the illusion of nested cosmic rings. Yet the visual effect is haunting and profoundly beautiful, as if the universe itself has arranged a perfect set of concentric circles, separated by hundreds of millions of light-years of space. The secondary ring is faint and difficult to observe in most images, requiring high-resolution telescopes to discern. It appears as a smaller, more distant halo of light that can just barely be seen through the nearly flawless blue ring of Hoag's object. The fact that it exists in the same line of sight creates a striking visual impression, making the galaxy appear as though it contains a miniature reflection of itself. This alignment is purely coincidental, an example of line-of-sight superposition, but the resulting aesthetic is uncanny, producing an eerie layering effect that reinforces the galaxy's reputation as one of the most visually captivating structures in the universe. For astronomers, the appearance of the second ring presents both an observational challenge and an opportunity. While the background galaxy does not interact with Hoag's object, it must be carefully accounted for in imaging and spectroscopic analysis. Distinguishing light from the secondary galaxy and from the outer ring of Hoag's object requires precise measurements of redshift, the degree to which light from each object has been stretched by the expansion of the universe. These measurements confirm that the two rings are separated by vast distances, with the background galaxy lying far beyond the 600 million light-year mark of Hoag's object. The existence of a second ring also heightens the sense of scale and isolation. Hoag's object itself is already extraordinary for its symmetry and rarity, but the fact that another ring galaxy aligns so perfectly along the same line of sight adds a dimension of cosmic coincidence that is both statistically improbable and visually haunting. It reminds us that the universe is layered in ways that can surprise even experienced astronomers. Light from billions of stars and countless galaxies can intersect across incomprehensible distances, creating illusions of proximity and alignment that are purely a product of perspective. From a visual perspective, this secondary ring intensifies the aesthetic impact of Hoag's object. The primary blue ring already surrounds the golden core with an almost perfect circle of stars. Through that ring, the faint halo of the more distant galaxy appears like a ghostly echo, emphasizing the original galaxy's circular perfection while adding a surreal, almost spectral quality to the image. For those studying images of Hoag's object, this feature reinforces the galaxy's reputation as a cosmic masterpiece, a visual paradox where isolation and alignment coexist in striking harmony. The presence of the background ring also reinforces the theme of layers in cosmic structure. Just as Hoag's object exhibits a clear inner and outer separation, the secondary galaxy adds a metaphorical layer to our understanding of the universe's complexity. It reminds us that our observations are always projections along vast distances, with galaxies overlapping in ways that are not physically connected but visually compelling. This layering underscores the idea that the universe is far richer and stranger than we might perceive from a single vantage point, full of coincidences and alignments that seem almost intentional in their visual impact. Furthermore, the secondary ring offers a subtle reminder of the depth of the universe. Hoag's object already challenges our understanding of formation and symmetry, but the glimpse of another ring far beyond it expands our perception of scale. If Hoag's object itself spans roughly 100,000 light-years and sits 600 million light-years away, the background ring lies at an even greater distance, suggesting that the universe contains not only vast numbers of galaxies but also layers of extraordinary, unusual structures waiting to be discovered. In this sense, the visual of a ring within a ring becomes a metaphor for the richness of cosmic exploration. Even when we think we have discovered something unique, the universe offers surprises at every scale and distance. Finally, the second ring reinforces Hoag's object's role as a source of wonder and curiosity. While astronomers are focused on understanding its formation, dynamics, and stellar populations, the ghostly appearance of another ring galaxy invites reflection on the serendipitous beauty of the cosmos. It is a visual reminder that the universe is not only a subject of scientific study but also an artistic masterpiece, where alignment, symmetry, and scale converge in ways that inspire awe. Even if the second ring has no physical connection to Hoag's object, its presence in images of the galaxy adds a layer of cosmic storytelling, highlighting the galaxy's otherworldly quality and deepening our appreciation of its complexity and mystery. One of the most striking aspects of Hoag's object is not only its rarity or mystery but its aesthetic perfection, which has captivated astronomers, astrophotographers, and the general public alike. There is an almost surreal beauty to this galaxy, a harmony of form, color, and geometry that makes it appear less like a naturally occurring cosmic structure and more like a deliberately crafted work of art. The symmetry, color contrast, and cosmic geometry of Hoag's object combine to create an object that is as visually mesmerizing as it is scientifically puzzling. The first element of its beauty lies in symmetry. Unlike the majority of galaxies, which are irregular, warped, or influenced by tidal interactions, Hoag's object exhibits a nearly perfect circular ring surrounding a spherical core. The outer ring forms a continuous loop without noticeable breaks or distortions, giving the galaxy a sense of balance and completeness that is exceedingly rare in the chaotic environment of the cosmos. Symmetry in galactic structures is not common because gravitational forces, random star formation, and past interactions tend to produce asymmetry over billions of years. Hoag's object, by contrast, has preserved a pristine, ordered structure, with the core and ring appearing as if meticulously aligned by some cosmic designer. This symmetry is not just visual, it extends to the underlying physics, suggesting a finely tuned balance between gravitational forces and orbital motions. The color contrast between the inner core and outer ring amplifies the galaxy's aesthetic impact. The central core glows with a warm, golden yellow light, composed of dense, older stars. Surrounding it is the luminous blue ring of younger, hotter stars, radiating a vibrant azure hue. The juxtaposition of warm and cool tones creates an immediate visual appeal, emphasizing both the separation of stellar populations and the depth of the structure. The golden core exudes stability and age, while the bright blue ring conveys youth, energy, and motion. Together, they produce a striking duality that is rare among galaxies, where colors often blend more gradually. In Hoag's object, the separation is sharp and dramatic, making the galaxy appear almost like a cosmic painting of light and color, suspended in space. Another aspect of Hoag's object's beauty is its geometric clarity. Beyond the symmetry of the ring itself, the galaxy presents a perfectly circular gap between the core and the ring. This empty space serves as a visual frame, isolating the golden core from the blue outer stars and enhancing the sense of order. It creates a natural focus, drawing the eye inward toward the luminous center while allowing the outer ring to encircle it like a celestial halo. The overall geometry, core, gap, and ring, is precise, almost mathematical, evoking the kind of clean lines and proportion found in classical art and design. The effect is further heightened by the galaxy's orientation, viewed nearly face-on from Earth. the circularity is maximized, presenting a perfect planar view that reveals the elegance of its structure in all its glory. The scale of the galaxy also contributes to its aesthetic allure. Spanning roughly 100,000 light-years across, Hoag's object is comparable in size to the Milky Way, yet its clarity of form is extraordinary. Most galaxies of this scale display irregularities: spiral arms that twist, elliptical forms that deviate, dust lanes that obscure regions, but Hoag's object is pristine. The enormity of its structure, combined with the perfection of its form, produces an almost surreal impression. A massive system that simultaneously embodies complexity, order, and visual harmony. Observers cannot help but marvel at the fact that billions of stars across such immense distances can align so perfectly to create such a strikingly beautiful and balanced form. There is also the ethereal quality of the galaxy's light. The warm golden glow of the core appears soft and steady, contrasting with the vibrant, almost electric radiance of the blue ring. The subtle differences in brightness across the ring, the slight gradients of color, and the way light seems to flow in a continuous loop give the impression of motion and life. The galaxy does not feel static. Instead, it seems suspended in dynamic equilibrium, with the inner and outer regions interacting subtly, producing a sense of cosmic rhythm. This interplay between stability and movement, old and new, warmth and coolness, adds layers of aesthetic sophistication to the galaxy's appearance. The alignment with the second ring galaxy in the background, faintly visible through the outer ring, adds an additional dimension to the visual experience. This creates an almost surreal nested effect, as if the universe itself has crafted a pattern of concentric rings, layered across hundreds of millions of light-years. While astronomically coincidental, the effect enhances the beauty of Hoag's object, reinforcing the perception that it is not merely scientifically remarkable but also aesthetically extraordinary. Even astronomers, trained to focus on data rather than aesthetics, have noted the galaxy's visual impact. The symmetry, the contrast between colors, and the precise circularity create an object that is immediately recognizable and deeply memorable. Its beauty is both structural and emotional. It captures attention through order and proportion, while simultaneously inspiring awe through its scale and the improbability of its existence. The galaxy's elegance bridges science and art, showing that even the most complex astrophysical systems can possess an almost perfect aesthetic quality. In short, Hoag's object is beautiful because of its rare combination of symmetry, color contrast, geometric precision, and cosmic scale. Its golden core, luminous blue ring, and the intervening void form a composition that is visually striking and harmonious. The galaxy's beauty is not merely surface level. It reflects the underlying cosmic processes and the delicate balance of forces that have maintained this extraordinary structure over billions of years. Hoag's object stands as a testament to the artistry inherent in the universe, a perfect marriage of physics and visual splendor, reminding us that the cosmos is not only a laboratory for scientific discovery but also a gallery of breathtaking natural masterpieces. Hoag's object is not just a visually captivating galaxy, it is also a crucial laboratory for astronomers studying galactic evolution. Its unusual structure, characterized by a dense, older core, a nearly perfect blue ring, and a clear gap separating the two, provides a natural experiment in which astrophysicists can examine how galaxies form, evolve, and interact over billions of years. By studying this unique system, astronomers gain insights that are often impossible to obtain from more conventional spirals or elliptical galaxies, which tend to be messy, crowded, and dynamically complex. One of the primary ways Hoag's object contributes to galaxy studies is through its distinct separation of stellar populations. Most galaxies contain overlapping distributions of stars of varying ages, making it difficult to isolate the processes that govern star formation, chemical enrichment, and gravitational dynamics. Hoag's object, by contrast, has an ancient, yellow-hued core composed of older stars and a luminous blue ring of much younger stars. This clear demarcation allows researchers to study each population independently, offering a rare opportunity to examine the properties of old stars in isolation and then compare them directly with the properties of young stars forming in a ring. This separation provides a living record of galactic evolution across different epochs, shedding light on how star formation may be triggered, sustained, or inhibited under varying conditions. Additionally, Hoag's object allows astronomers to test competing models of galaxy formation. The collision theory and gravitational resonance theory, while plausible, both face limitations when applied to this galaxy, as discussed earlier. By studying Hoag's object in detail, Through spectroscopy, photometry, and kinematic analysis, astronomers can gather empirical data about the velocities, chemical compositions, and ages of stars in both the core and ring. These measurements help evaluate the plausibility of each theory and refine simulations of galaxy evolution. For instance, understanding the mass distribution and orbital dynamics of the galaxy can reveal whether internal resonance mechanisms could realistically produce the observed ring, or whether some past interaction is required. In this way, Hoag's object acts as a benchmark for testing theoretical models, pushing our understanding of galactic physics to its limits. The galaxy also provides insights into star formation in extreme environments. The blue ring of Hoag's object is a site of active, high-mass star formation occurring in an almost perfectly circular pattern. Studying the rate of star formation, the density of gas clouds, and the feedback processes in this isolated ring can reveal how stars form under unusual conditions. Observing such a controlled environment, without the chaotic overlap of spiral arms, bars, or mergers found in other galaxies, allows astronomers to disentangle factors that influence the birth of stars, including gas density, gravitational forces, and potential external triggers. In essence, Hoag's object provides a natural laboratory to explore star formation in a nearly idealized setting. Kinematic studies of the galaxy, tracking the motions of stars within the ring and the core, also contribute to our understanding of gravitational dynamics and stability. The near-perfect circularity of the ring raises questions about how such structures can remain stable over millions of years. By mapping the velocities of stars, astronomers can infer the gravitational potential of the galaxy, the distribution of dark matter, and the forces maintaining the separation between the core and the ring. These studies inform broader models of galactic stability, helping researchers understand how unusual structures can persist in a universe dominated by interactions, collisions, and turbulence. Hoag's object also plays a role in refining our understanding of galaxy classification. The traditional Hubble sequence categorizes most galaxies as spiral, elliptical, or irregular, but ring galaxies like Hoag's object challenge this system. By studying its morphology, astronomers can explore how classification schemes might accommodate rare or extreme cases, and whether there are undiscovered processes or subcategories that need to be considered. In this sense, Hoag's object pushes the boundaries not only of galactic physics but also of the frameworks we use to describe and categorize the cosmos. Beyond the purely scientific, Hoag's object has inspired the development of observational techniques and instrumentation. Because of its faint, isolated structure and the need for high-resolution imaging to discern the core and ring, it has been a target for advanced telescopes, adaptive optic systems, and spectrographs. Observations of this galaxy have pushed the limits of what modern technology can achieve, driving improvements in image resolution, photometric sensitivity, and kinematic mapping. In this way, Hoag's object has indirectly influenced the broader field of astronomy by motivating technological innovation. The galaxy's unique properties also enable comparative studies with other ring galaxies. By contrasting Hoag's object with systems like the Cartwheel Galaxy or other collisional rings, astronomers can explore the diversity of ring formation processes, environmental influences, and evolutionary outcomes. Understanding why some rings are distorted while Hoag's object remains near-perfect provides clues about the conditions required for long-term stability and symmetry in galactic structures. These comparative analyses help refine theories of cosmic structure formation, bridging the gap between rare anomalies and more typical galactic systems. Finally, Hoag's object provides a window into extreme cosmic physics. Its combination of isolation, symmetry, and clear stellar separation allows researchers to explore phenomena such as the influence of dark matter on orbital stability, the propagation of density waves, and the limits of gravitational resonance. Each insight gleaned from the galaxy contributes to our understanding of universal principles, helping scientists refine models that apply not just to ring galaxies but to the broader population of galaxies across the cosmos. In summary, Hoag's object is far more than a visual curiosity. It is a scientific treasure trove. Its unusual structure, isolation, and symmetry make it an ideal laboratory for testing theories of galactic evolution, star formation, gravitational dynamics, and cosmic classification. By studying this galaxy, astronomers can explore questions that cannot easily be answered using more conventional galaxies, making it an indispensable object for advancing our understanding of how galaxies form, evolve, and interact. In many ways, Hoag's object is a natural experiment on a scale and precision that human-made laboratories could never replicate, offering insights that span billions of years of cosmic history. Hoag's object, in all its symmetry and perfection, does more than challenge our understanding of galactic evolution. It also raises profound questions about the underlying physics that govern the universe. While much of astrophysics relies on well-tested theories of gravity, star formation, and cosmic structure, galaxies like Hoag's object remind us that the cosmos may still harbor unknown dynamics, subtle processes, or boundary conditions that are not fully captured in current models. Studying such unusual systems offers an opportunity to explore these frontiers, potentially leading to insights that extend beyond a single galaxy to the fundamental laws of physics themselves. One area of implication lies in gravitational dynamics. Conventional models assume that the motion of stars and gas within galaxies is largely determined by the visible mass, stars, gas, dust, and the inferred presence of dark matter. Yet Hoag's object presents an unusual combination of stability, symmetry, and isolation that is difficult to reproduce even in simulations that account for dark matter halos. The outer ring maintains a near-perfect circular orbit around the central core, and the gap between core and ring remains largely empty despite the strong gravitational pull of the dense central region. This stability over billions of years challenges astrophysicists to reconcile how gravitational forces, orbital motion, and galactic mass distribution can combine to produce such enduring equilibrium. Could there be subtle gravitational mechanisms at work, perhaps related to dark matter distribution, resonance effects, or previously unrecognized forces, that allow matter to self-organize in such an orderly manner? Hoag's object also prompts questions about the dynamics of star formation. The sharp separation between the old, yellow stars in the core and the young, blue stars in the ring is striking. In most galaxies, star formation is a more continuous process, influenced by gas density, turbulence, and feedback from existing stars. The nearly perfect confinement of star formation to the ring suggests that there may be mechanisms capable of channeling gas into specific orbits while simultaneously suppressing star formation elsewhere, a level of control that is not fully understood. This raises the possibility that our current models of star formation, which are generally statistical and based on large-scale turbulence and gas density thresholds, may need refinement to account for scenarios in which highly organized patterns emerge on galactic scales. The galaxy's symmetry also intersects with broader questions about cosmic structure formation. In a universe dominated by chaotic interactions, gravitational perturbations, and stochastic events, why would such a pristine system emerge? Does Hoag's object represent a rare statistical fluke, or does it hint at underlying organizing principles in galactic physics that we have yet to uncover? The near-perfect ring, the clear separation of stellar populations, and the persistence of the gap over millions of years all suggest that there may be constraints or dynamics in the laws of physics that can produce extreme order under specific conditions. If such processes exist, they could have implications not only for ring galaxies but also for understanding the distribution of matter, energy, and angular momentum in all galaxies. Another implication concerns the interaction between visible and dark matter. Dark matter is thought to dominate the mass budget of galaxies and plays a critical role in shaping their evolution. In Hoag's object, the ring's stability implies that the gravitational potential well created by both the visible mass and the dark matter halo is extraordinarily uniform. This raises questions about the distribution and behavior of dark matter in rare, highly ordered systems. Could there be forms of dark matter interaction or density profiles that promote symmetry and stability in ways we have not yet observed elsewhere? Studying Hoag's object in detail may help constrain models of dark matter distribution on galactic scales, providing clues about the invisible scaffolding that shapes the cosmos. The galaxy also encourages theorists to explore the limits of current gravitational simulations. When modeling ring galaxies, astrophysicists must input initial conditions for mass distribution, velocity profiles, and gas density, then simulate billions of years of evolution. Reproducing Hoag's object's precision is extremely challenging, suggesting that current simulations might be missing factors, simplifications, or physical processes that become critical in rare cases. This could include more subtle gravitational resonances, interactions with diffuse intergalactic material, or feedback mechanisms from stellar winds and radiation that are not fully captured in standard models. In this sense, Hoag's object acts as a stress test for the laws of physics as applied to galaxy formation. Beyond gravity and star formation, the The galaxy raises questions about cosmic symmetry and self-organization. The degree of order seen in Hoag's object is extraordinary. While nature often produces beauty through chaotic processes that accidentally converge on pleasing patterns, the combination of size, symmetry, and isolation in this galaxy is extreme. This prompts deeper questions. Are there physical constraints that favor such outcomes under certain conditions? Could large-scale electromagnetic fields, rotational dynamics, or other less studied forces play a role in organizing matter in ways that complement gravity? Each of these possibilities, while speculative, opens avenues for exploring novel physics inspired by observation rather than theory alone. Finally, studying galaxies like Hoag's object could have broader implications for cosmology. If highly ordered systems can exist and persist over billions of years, this might influence our understanding of how galaxies evolve statistically in the universe. Are there more such galaxies waiting to be discovered, obscured by distance, orientation, or faintness? Could these rare structures reveal new constraints on the large-scale distribution of matter, the evolution of angular momentum, or the interplay between dark and visible matter? In short, unusual galaxies challenge not only our models of individual systems but also our broader conception of how structure arises in the cosmos. In conclusion, Hoag's object hints at unknown dynamics in both gravity and star formation, forcing astrophysicists to confront the limitations of current models. Its symmetry, isolation, and stellar separation suggest mechanisms that are either exceptionally rare or entirely unrecognized, and studying it may illuminate hidden principles governing the behavior of matter on galactic scales. By pushing the boundaries of observation, simulation, and theory, this extraordinary galaxy serves as both a mystery and an inspiration, reminding us that even in a universe dominated by known physical laws, nature can produce extreme order, beauty, and complexity that challenge our understanding and invite us to explore the physics we have yet to fully grasp. When placing Hoag's object in the broader context of galactic morphology, it becomes clear just how unusual it truly is. Ring galaxies, though rare, are a known phenomenon in the universe, often resulting from interactions or collisions between galaxies. One of the most famous examples is the Cartwheel Galaxy, located approximately 500 million light-years away in the constellation Sculptor. The Cartwheel Galaxy exhibits a dramatic ring structure, but when compared to Hoag's object, the differences are striking and instructive for understanding the latter's uniqueness. The Cartwheel Galaxy formed through a relatively well-understood galactic collision. A smaller intruder galaxy passed through the center of a larger spiral, generating an outward propagating density wave. This wave triggered a burst of star formation in the form of the bright, blue outer ring that dominates its appearance. In addition to the ring, the cartwheel exhibits spokes of stars, irregularities, and distortions, all characteristic of the chaotic dynamics inherent to collision-driven formation. These features reveal the violent history of the galaxy and reflect the energetic redistribution of matter during and after the collision. Hoag's object, by contrast, presents an almost entirely ordered and symmetric structure. Its ring is perfectly circular, the gap between the core and the ring is nearly empty, and the core itself appears undisturbed. Unlike the cartwheel, there are no spokes, tidal tails, or visible irregularities that suggest a violent past. This contrast highlights the puzzle of Hoag's object. While the cartwheel demonstrates what a collision-generated ring typically looks like, Hoag's object shows none of the hallmarks expected from such a process. Its perfection raises the possibility of alternative formation mechanisms, such as internal gravitational resonance or processes that we have not yet discovered. Other ring galaxies provide additional points of comparison. For instance, galaxies catalogued as M0644-741 or NGC 922 also show ring structures formed via collisions or resonances, but all exhibit some irregularity, warped rings, asymmetric star formation, or disrupted cores. In each case, the ring is either not perfectly circular or the central region shows signs of disturbance. Hoag's object stands out because of its rare combination of circularity, separation, and isolation, features that are nearly absent in other observed ring systems. Its symmetry is almost uncanny when juxtaposed with the more chaotic appearance of other ring galaxies. The comparison also underscores how Hoag's object challenges existing classification schemes. Ring galaxies formed through collisions tend to fit a predictable pattern: central core distorted, outer ring clumpy, and remnants of the interacting galaxy nearby. Hoag's object defies these expectations, suggesting either an unusual formation history or an extreme case of internal regulation that has maintained order over billions of years. While the cartwheel and similar galaxies tell us what ring formation typically looks like under known physical processes, Hoag's object reminds us that the universe can produce outliers that push the boundaries of understanding. Studying these differences provides insight into the diversity of galactic behavior. The cartwheel demonstrates the impact of external events like collisions, while Hoag's object emphasizes the potential role of isolation, internal dynamics, and resonance. By contrasting these galaxies, astronomers can refine models of ring formation, explore the limits of gravitational influence, and test whether internal versus external mechanisms dominate under different conditions. It also helps highlight the statistical rarity of Hoag-type systems. Fewer than 0.1% of galaxies display a ring as symmetric and undisturbed, emphasizing that Hoag's object occupies a special niche in the galactic population. Finally, these comparisons reinforce Hoag's object's role as a cosmic benchmark. While the cartwheel and other collisional rings provide clear examples of violent, high-energy formation processes, Hoag's object represents a class of galaxies where symmetry, order, and isolation prevail. This makes it invaluable for testing theories of galactic evolution, resonance phenomena, and the long-term stability of stellar systems. Its contrast with more typical ring galaxies highlights not only its beauty but also its scientific significance, serving as a reminder that nature can produce both chaos and perfection in the same cosmic neighborhood. Hoag's object captivates astronomers in ways that go beyond its rarity or distance. While many galaxies are fascinating for their dramatic collisions, sprawling spiral arms, or chaotic irregularities, Hoag's object stands out because of its simplicity and symmetry, qualities that seem almost alien in a universe defined by turbulence and complexity. Its appeal lies not just in its aesthetic beauty, but in the profound scientific mystery it embodies, an ongoing puzzle that challenges fundamental assumptions about how galaxies form, evolve, and maintain order over billions of years. The galaxy's geometric simplicity is striking. With a nearly perfect circular ring surrounding a dense, spherical core, and a pristine gap in between, Hoag's object exhibits an almost minimalist design. There are no spiral arms twisting into chaos, no tidal tails marking past collisions, and no clumps of irregular star formation to disrupt the symmetry. This extreme simplicity forces astronomers to confront questions about how order arises in systems dominated by gravity, where even small perturbations over cosmic timescales usually generate irregularities. It is the very perfection of the structure that makes the galaxy a puzzle. If galaxies are shaped by random collisions, mergers, and gravitational interactions, why has Hoag's object maintained such uniformity? The symmetry of the galaxy is equally compelling. The ring forms a nearly flawless circle, and the central core is perfectly aligned within it. Symmetry in the cosmos is rare, especially on the scale of tens or hundreds of thousands of light-years. In other galaxies, even small asymmetries are amplified over millions of years by gravitational forces, stellar motions, and interactions with nearby galaxies. The degree of balance seen in Hoag's object is therefore not just unusual, it is almost miraculous, given the chaotic environment of the universe. For astronomers, this symmetry raises questions about the underlying mechanisms that can stabilize matter over vast distances and timescales, and whether new physics or exceptional conditions are required to explain it. Another factor contributing to astronomers' fascination is the clear separation of stellar populations. The golden, older stars in the core are isolated from the hot, blue, younger stars in the ring. This sharp division is unusual because, in most galaxies, star formation occurs more continuously and stars of different ages overlap spatially. Hoag's object, with its neatly partitioned populations, provides a natural laboratory to study stellar evolution in two distinct regions under very different conditions. The simplicity of the system allows researchers to isolate variables and analyze processes such as star formation, gas dynamics, and gravitational influences without the confounding complexity present in most other galaxies. Its rarity further enhances the galaxy's allure. Fewer than 0.1% of known galaxies exhibit such a symmetric ring, and even among those, few are as isolated or undisturbed as Hoag's object. Its scarcity means that every observation, every measurement, provides potentially unique insight into galactic evolution. Astronomers are drawn to the challenge of explaining how such a galaxy could form and persist, knowing that it represents one of the most extreme examples of cosmic organization ever observed. Hoag's object also captivates because it is a mystery that has resisted easy explanation for decades. Discovered in 1950 by Arthur Hoag, it has since been studied extensively, yet no theory, neither collision nor gravitational resonance, fully accounts for its structure. The persistent gaps in understanding, combined with the galaxy's pristine appearance, make it a source of enduring curiosity. Scientists are not merely observing beauty. They are facing a cosmic conundrum that forces them to reconsider assumptions about galaxy formation, stability, and evolution. The galaxy's aesthetic appeal and scientific intrigue are deeply intertwined. Its visual harmony draws the eye, but each aspect of its design, the circular ring, the isolated core, the gap, and even the faint secondary ring in the background, also encodes information about the forces shaping the galaxy. Astronomers are motivated not only by the desire to categorize or model it, but also by the intellectual challenge it represents, a reminder that the universe can produce perfection that both inspires and defies comprehension. Finally, Hoag's object embodies a sense of cosmic humility. It reminds astronomers that, despite centuries of observation and advanced simulations, the universe still contains systems that defy prediction. Its simplicity is deceptive. While it appears orderly at first glance, it raises questions that are deeply complex. This duality, visual clarity masking profound physical mystery, is part of what keeps astronomers returning to study it. Each new observation can reveal subtle details that might hint at the processes responsible for its creation, yet the full picture remains elusive, maintaining its status as one of the universe's most captivating and enigmatic structures. In summary, Hoag's object captivates astronomers because of its simplicity, symmetry, rarity, and enduring mystery. Its nearly perfect ring, isolated core, and clean separation of stellar populations make it both a visual and scientific marvel. The galaxy challenges fundamental assumptions about galactic dynamics and evolution, offering a cosmic puzzle that continues to engage, inspire, and frustrate the scientific community. Its allure lies in the combination of visual elegance and the unanswered questions it poses, a perfect example of how beauty and mystery intersect in the cosmos. The continued fascination with Hoag's object is matched by the promise of future research, as new observational tools and next-generation telescopes are poised to probe the galaxy with unprecedented precision. While existing instruments like the Hubble Space Telescope have revealed remarkable details about the structure, color, and stellar populations of Hoag's object, many questions remain unresolved. The advent of advanced facilities such as the James Webb Space Telescope, JWST, next-generation ground-based observatories, and powerful spectrographs offers the possibility of unveiling insights that were previously beyond reach, potentially shedding light on its formation, composition, and dynamics. One of the primary avenues of future research is high-resolution infrared imaging. Unlike Hubble, which observes primarily in optical and ultraviolet wavelengths, JWST is optimized for infrared observations. This capability allows astronomers to peer through dust and detect cooler stellar populations and faint gas structures that may exist between the core and the outer ring. By mapping the distribution of gas and dust with high fidelity, JWST could reveal whether there are subtle features, such as faint tidal streams, residual gas bridges, or small satellite objects, that have so far escaped detection. Such discoveries would be crucial for testing formation theories, particularly the gravitational resonance hypothesis, as the presence or absence of certain structures could either support or contradict the idea that internal dynamics shape the ring. Spectroscopic observations using JWST or ground-based extremely large telescopes, ELTs, will also be transformative. By analyzing the light from stars in both the core and the ring, astronomers can measure stellar velocities, chemical abundances, and ages with unprecedented accuracy. This information is critical for understanding the history of star formation in the galaxy and for distinguishing between competing formation scenarios. For example, if the ring stars show a continuous chemical gradient consistent with enrichment from the central core, it could suggest internal processes like resonance-driven migration. Alternatively, an abrupt difference in chemical composition might hint at an external origin, such as a past collision or accretion event. Detailed spectroscopy could therefore provide the first definitive clues about how Hoag's object acquired its unique structure. The study of dark matter distribution is another frontier that upcoming instruments can address. Precise measurements of the motion of stars in the ring and the core can be used to model the galaxy's gravitational potential, revealing the configuration of dark matter that underpins its stability. Current models can only estimate the dark matter halo, but higher-resolution kinematic data could determine whether the dark matter is distributed uniformly or if unusual concentrations exist that might help explain the perfect circularity of the ring. Understanding dark matter's role in maintaining the galaxy's equilibrium could have broader implications for cosmology, providing insights into the invisible scaffolding that shapes all galaxies. Another promising avenue is multi-wavelength observation, combining optical, infrared, radio, and even X-ray data. Each wavelength probes different physical processes. Optical and infrared reveal stars and dust. Radio traces neutral hydrogen gas that fuels star formation, and X-ray observations can detect high-energy phenomena such as supernova remnants or hot gas halos. By integrating data across the electromagnetic spectrum, astronomers could build a comprehensive 3D model of Hoag's object, mapping its mass, star formation history, and dynamic processes in unprecedented detail. This holistic approach could answer questions about how the galaxy maintains its symmetry and how matter circulates between the core and the ring. The next generation of extremely large telescopes, such as the 30-meter telescope, TMT, or the European Extremely Large Telescope, EELT, will provide the spatial resolution necessary to observe individual stars in the outer ring. This would allow astronomers to directly measure star formation rates and determine whether star formation is occurring uniformly along the ring or if subtle variations exist. Observing individual stars would also enable the study of stellar evolution in an environment remarkably isolated from galactic chaos, offering a natural laboratory for testing models of how stars form and evolve under highly organized conditions. Another exciting possibility is the use of gravitational lensing studies if an intervening mass were fortuitously aligned along our line of sight. While rare, gravitational lensing could magnify certain features of the galaxy, providing additional structural details otherwise impossible to resolve. Even without lensing, the precision of JWST and ELTS will allow astronomers to investigate subtle features such as stellar density waves, faint secondary rings, or minor asymmetries that could hold clues to the galaxy's history. Finally, future research may involve long-term monitoring. By observing Hoag's object over decades, astronomers can detect changes in brightness, new supernova events, or subtle motions within the ring. While these changes occur over vast timescales, even small variations can inform models of stellar evolution, gas dynamics, and galactic stability, gradually building a dynamic picture of the galaxy rather than a static snapshot. In summary, upcoming telescopes like JWST and ELTS, combined with multi-wavelength analysis and advanced spectroscopic studies, have the potential to revolutionize our understanding of Hoag's object. They may answer long-standing questions about its formation, reveal the role of dark matter in maintaining its symmetry, map the distribution of gas and stars with unparalleled precision, and even uncover subtle phenomena that challenge current theories of galaxy evolution. Every new observation promises to peel back a layer of mystery, bringing us closer to understanding how such an extraordinary and isolated system could exist. Hoag's object is not just a relic of the distant universe, it is a living laboratory, waiting for the next generation of instruments to illuminate its secrets. Hoag's object, in all its elegance and mystery, serves as a profound reminder of the vast unknowns that still exist in our universe. Despite decades of observation, advanced modeling, and theoretical study, this galaxy continues to elude full explanation. Its nearly perfect symmetry, the stark separation between old and young stars, the pristine circular ring, and even the ghostly presence of another ring galaxy in the background collectively defy simple categorization. In this sense, Hoag's object is not just a single cosmic curiosity. It is a symbol of the universe's capacity for surprise, complexity, and beauty, highlighting how much there still is to learn about the cosmos. The galaxy's perfection, its luminous yellow core encircled by a flawless ring of young blue stars, illustrates the duality of nature, chaos and order coexisting in a delicate balance. Most galaxies are messy, products of collisions, mergers, and turbulent star formation. Yet Hoag's object stands as an example of cosmic precision, a system that seems to operate according to rules we are only beginning to understand. Its very existence challenges our assumptions about galactic evolution and star formation, inviting astronomers to consider possibilities beyond conventional models. Each unanswered question, how the ring formed, why the core remained undisturbed, what mechanisms maintain its symmetry, reflects a gap in our knowledge, a frontier for future exploration. Yet the wonder of Hoag's object is not solely scientific. Its aesthetic harmony, visible even across 600 million light-years, inspires awe in anyone who studies it. The contrast of colors, the circularity of the ring, the isolation of the core, and the subtle layering with the distant secondary galaxy create an image that feels almost otherworldly. It reminds us that the universe is not only a laboratory for physics and astronomy but also a canvas for visual grandeur, capable of producing structures that are simultaneously functional, intricate, and breathtakingly beautiful. This combination of intellectual intrigue and visual splendor makes Hoag's object uniquely compelling, capturing the imagination of both scientists and the public alike. Hoag's object also exemplifies the scale and temporal depth of cosmic phenomena. The light we see today left the galaxy 600 million years ago, offering a window into a distant epoch of the universe. Its stars, numbering in the billions, have followed orbits and evolutionary paths that span hundreds of thousands to billions of years. Observing this galaxy allows us to peer into deep time, to witness processes and structures that dwarf human experience, and to reflect on the immense patience and precision required for such a system to form and persist. In this way, Hoag's object is a humbling testament to the vast scales of space and time over which cosmic order can emerge. At the same time, the galaxy symbolizes the limits of human understanding. Despite all our technological advancements, from ground-based observatories to space telescopes like Hubble and soon JWST, there remain aspects of Hoag's object that we cannot explain. Its formation remains debated, its dynamics partially mysterious, and its isolated perfection continues to challenge prevailing theories. In this sense, it embodies the frontier of knowledge, a reminder that the universe is far larger, stranger, and more complex than our current frameworks can fully describe. Each observation is both an answer and a question, a step forward that uncovers new mysteries lurking beneath the surface. Moreover, Hoag's object encourages a sense of curiosity and humility in scientific inquiry. It illustrates that nature often produces phenomena that are not only rare but exquisitely ordered, prompting us to expand our theoretical models and observational techniques. The galaxy is a catalyst for innovation, inspiring astronomers to develop better simulations, more sensitive instruments, and more nuanced theories about star formation, galactic dynamics, and dark matter distribution. Its persistence as an unsolved puzzle demonstrates that even in a universe governed by physical laws, outcomes can be far more intricate and unexpected than anticipated. In a broader philosophical sense, Hoag's object invites reflection on the mystery of the cosmos itself. It is a reminder that, despite centuries of astronomical study, the universe still holds secrets that challenge our imagination and intellect. Its elegance, rarity, and incomprehensible scale provoke wonder not just at the mechanisms that formed it, but at the sheer vastness of the cosmos, a realm where perfection, chaos, beauty, and mystery coexist. In this way, Hoag's object becomes more than an astronomical object. It becomes a symbol of the boundless curiosity, awe, and humility that the study of the universe demands. Ultimately, Hoag's object stands as a cosmic beacon of possibility and discovery. It tells us that even in the immense expanse of space, nature can craft structures of extraordinary precision and beauty, and that the universe still harbors questions that are waiting for the right instruments, theories, and insights to unlock. As astronomers prepare to study it with next-generation telescopes and as theoretical models continue to evolve, Hoag's object will remain a testament to the enduring mystery, elegance, and wonder of the cosmos. A galaxy that defies explanation, captivates the mind, and inspires the imagination, inviting all who study it to look deeper into the universe and contemplate the extraordinary complexity of the reality we inhabit. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.